All right, so the next type of motion that we're going to talk about is called simple harmonic motion. And to start with, let's talk about the two types of simple harmonic oscillators that we're going to deal with. So again, you can see the abbreviations that we'll often use just to simplify writing all this out. Well, the two simple harmonic oscillators that we're going to deal with, one type is basically going to be situations where things bounce back and forth. So the most obvious example of that is a spring and mass system. So put a mass on the end of a spring and it'll bounce back and forth. It does that because there's a restoring force that's trying to return the system to equilibrium. Now, the equilibrium here is just like any static equilibrium. It's trying to get it back to the point where the forces all cancel out, and so the mass will just rest there. The second type of oscillator that we'll deal with is one that swings back and forth. And so the sort of prototypical simple harmonic oscillator that swings back and forth is the simple pendulum. And again, oscillators that swing back and forth do so because there's a restoring torque trying to return the system to equilibrium. So again, for our simple pendulum, the equilibrium position is basically just letting the string hang straight down, right? If you let the string hang straight down, leave it alone, it's just going to stay there. So that's the equilibrium for the system. And as you pull the mass away from hanging vertically, and you pull it up in this direction and let it go, then what you're going to see ends up happening is that there's a restoring torque that's trying to get the system back to just hanging vertically. All right, so these are the two types of simple harmonic oscillators that we'll talk about. Simple harmonic motion for both types is sinusoidal motion. So because we have those restoring forces or restoring torques, and those forces and torques happen to be proportional to the displacement. So the farther you pull the mass away from equilibrium, the larger the force is that's trying to get it back to equilibrium. Then you have sinusoidal motion that's going to take place. And so when you plot out for any of our simple harmonic oscillators, when you plot out the displacement on the vertical axis versus time on the horizontal axis, what you see is the bouncing back and forth shows up as a sine or cosine curve. Amplitude is the name that we're going to give to the maximum displacement. And then the time to go from, say, one positive peak to positive peak, that's the period. Now it would be the same time to go from trough to trough, and the same time to go from crossing this curve with a downward slope to crossing this curve with a downward slope the next time. All those times, all those lengths of times are equal to the period. So our equation that describes this sinusoidal motion. So there's two of them. We'll see that really all that we're changing is just the whether we're bouncing back and forth or swinging back and forth. And for a linear simple harmonic oscillator, that's the one that bounces back and forth along a line, then what we've got is some displacement from equilibrium. So again, this is really a displacement rather than a position. So the displacement from equilibrium as a function of time is given by, A here is the amplitude. Again, it's just a way of saying the maximum displacement. This is a linear displacement, so this is going to be x max. We're going to leave this as a cosine function. And then everything that we plug into the cosine function is known as the phase, and it's basically got three parts. There's the angular frequency. So up until now when we've used omega, we've meant either angular velocity or angular speed. And now we're going to use it a third way. We're going to use it as the angular frequency. We'll come back and define that in a second. But so there's the angular frequency. That's going to have units of radians per second. Time has units of seconds, so obviously the product of those two is going to have units of radians. And then phase shift will also have units of radians. And the phase shift is just telling me about, so a cosine curve at t equals 0, if it's not at its maximum, that means that there has to be a phase shift here to get away from its peak, because cosine of 0 should be a maximum. So if our cosine curve isn't at a maximum at t equals 0, then that means we'll have some non-zero phase shift involved in the problem. So this is for our linear simple harmonic oscillator. We also have an angular simple harmonic oscillator. Those are the ones that swing back and forth. And again, you'll notice that there's only a couple real differences. One is that instead of keeping track of a linear displacement, I'm keeping track of an angular displacement from equilibrium at time t. My amplitude, again, that's still the maximum displacement. It's just now I have an angular displacement, so this is now theta max, which is the maximum angle, say, away from the vertical that my simple pendulum ever reaches. Again, I've still got a cosine function, and everything's the same inside the phase. So it's still the angular frequency times time plus the phase shift. So what is this? What is the angular frequency and how does it relate to the period? Well, we know that the period, we use big T for that, and that's the time it takes to complete one cycle. The frequency, that's F, that's the number of cycles per second. That has units of inverse seconds or hertz. And then the angular frequency, omega, is the rate of change of our sine wave. So that's the radians per second. So the way these things all relate, and it doesn't really matter, they're really all just the same equation, you're just rearranging what you're solving for. But I can relate the period to the frequency because the period's just 1 over the frequency, right? Units of seconds, units of 1 over seconds, that makes sense. Again, to go from the frequency to omega, well, omega is just 2 pi times the frequency. So it's basically 2 pi radians times 1 over seconds gets me my units of radians over seconds. And so all of these are really just the same sets of equations, just this one solved for the period, this one solved for the frequency, this one solved for omega. And so this tells us how our three things relate. So you notice that the period is 1 over the frequency, and it's 2 pi over omega, 2 pi over the angular frequency. And so one of the things that we'll have to do is we'll have to pay attention to units to make sure we're talking about the frequency or the angular frequency. Alright, so for my linear simple harmonic oscillator, we said here's what the displacement as a function of time is. Well, obviously, if I take the derivative of this with respect to time, I can get the velocity. If I take the derivative of the velocity with respect to time, I can get the acceleration. So when you go through that process, again, you take the derivative of cosine, you get minus sine, you take the derivative inside our phase here, and I get another omega that comes out front. So you can sort of walk yourself through taking the derivative of this function to get the velocity. You do it again to get the acceleration, and what you notice is, well, a cosine omega t plus phi, that is the position. And so this form here that says the acceleration is equal to negative omega squared times the position, that's going to be true for any simple harmonic oscillator. So when you solved, say, Newton's second law, right? If you set up your Newton's second law and solve for the acceleration, anytime you've got a simple harmonic oscillator, when you solve for the acceleration, you would get something that had this expression. So negative omega squared times the position. For our linear simple harmonic oscillators, again, that position, right, that maximum displacement, that's just another way of saying the amplitude. The maximum speed, well, again, the maximum speed says I don't care about the sign. I don't care whether this is plus or minus over here. And I don't care about this function over here other than the fact that it's at its maximum when it equals 1. So the maximum speed is just going to be what you've got sitting right there. So the maximum speed for your linear simple harmonic oscillator is going to be omega times the amplitude. Your maximum acceleration, again, don't worry about the minus sign. Cosine's at a maximum when it's 1. So the maximum acceleration of your simple harmonic oscillator is going to be omega squared times a. So here's the relation that we've got that we can use to say, hey, if you know Right, so if we know what omega is, and we know how far we pulled out our, say, simple harmonic oscillator, so what the amplitude was when we let it go, then we can figure out what its maximum speed will be. We can figure out what the maximum acceleration is going to be acting on. If we think about our angular simple harmonic oscillators, we can do the same thing. So we said here is the angular displacement as a function of time. Again, when I take the derivative of that, I get omega. Now, since we're already using omega as the angular frequency, we use capital omega to talk about the angular velocity. So in the same way this is linear displacement, linear velocity, linear acceleration, this is angular displacement, angular velocity, angular acceleration. And the only thing we're doing is just switching around to the capital omega because we're already using lowercase as the angular frequency here. But I can take the derivative of the angular velocity with respect to time to get the angular acceleration. Again, you see that these equations work out exactly the same. And again, I have that the angular acceleration for my angular simple harmonic oscillator always has to have this form. Negative omega squared, again, just some constant, times the angular displacement. And the one thing we'll see for a lot of angular simple harmonic oscillators is that they're not quite proportional to theta, except when theta is a small angle. So we end up using the small angle approximation very often when we're dealing with angular simple harmonic oscillators. Again, I can think about the maximum angular displacement, that's the amplitude, the maximum angular speed, that's going to be the omega, the angular frequency, times the amplitude, and the maximum angular acceleration, that's going to be the angular frequency squared times the amplitude. So if I think about sort of graphing out those three functions, and we'll just deal with our spring and mass system, so looking at our linear simple harmonic oscillator, though I get exactly the same functions if I were to do this with the angular simple harmonic oscillator. This is what the functions are going to look like. Now again, I can have these things so that the heights of these functions are very different, but in terms of how they relate in time, there's actually a very particular pattern that we can pay attention to here. So one thing is, let's just pick this particular point, because it happens to be where the displacement curve, that's the blue curve, is at its maximum in the positive direction. And the first thing we'll do is say, well, to go through one period from this point requires going through all the way down, maximum displacement in the negative direction, coming all the way back up to maximum displacement in the positive direction. So from this line on my graph to this line on my graph is one full period t. A couple of interesting points here. So one is that at both these two, the point that I start and the point that I finish, what you'll notice is I'm at my maximum positive displacement, but my velocity at both those points is 0. And the acceleration is at its maximum value, but in the negative direction. And again, this makes sense because it says, hey, if you've pulled your spring out as far as it can go, so it's at the amplitude value in the positive direction, there's two things going on. One is the spring is trying to pull it back towards equilibrium, so it's pulling it in the negative direction, so that sign makes sense. And the farther you pull it away, the larger the acceleration is going to be. So it makes sense that this is at its maximum positive value, the displacement's at its maximum positive value, the acceleration's at its maximum negative value. The other thing is that when it gets out to amplitude, that's the point where it's going to turn around and start coming back. And in order to turn around, it has to stop. So it also makes sense that the velocity is equal to 0 at exactly that same point in time. And that's true for both of these 2 points. Now if I go 1/4 of the way through the period, what I notice is now I'm at the position where my displacement is 0. That means I'm back at equilibrium. The acceleration is also 0. Again, that tells me I'm back at equilibrium because There's no force acting on the spring anymore, or no force acting on my mass anymore. And I'm at the maximum velocity. In this case, it happens to be the maximum negative velocity. And again, if I think about having pulled the spring out to some maximum positive value, again, it makes sense that as it comes back through equilibrium, it's moving in the negative direction as fast as it's going to when it gets to that equilibrium point. I go another quarter of the way through the period. That lets it go from equilibrium over to the negative amplitude. So the maximum displacement away from equilibrium in the negative direction. And again, what I see here is maximum displacement from equilibrium in the negative direction. Now I have the maximum acceleration in the positive direction. And again, that makes sense because the spring force is trying to pull it back towards equilibrium. And again, my speed is 0 because the block's got to stop to turn around. Another quarter of the way through the period. Now my block is coming back through equilibrium. It's moving in the positive direction, so it has a positive speed. At equilibrium, its displacement 0, the acceleration 0. So this is where the acceleration is about to change from speeding the block up to slowing the block down. Because it's about to go from positive velocity, negative acceleration. That's going to slow my block back down. And so I'm back at equilibrium now, moving back towards my initial position back here to get to back to my positive maximum amplitude. So you can see that these these curves line up in a very special way. The displacement and velocity curve is out of phase by 90 degrees, so that when one is at its maximum amplitude, the other one's 0. And then the displacement and acceleration curve are out of phase by 180 degrees. So they're both at maximum value at the same time, but one is positive and the other one's negative. So again, when I think about my spring and mass system, the angular frequency for my spring and mass system, if I were to work my Newton's second law problem and solve for the acceleration, I would get that the acceleration is equal to negative k over m times x. And so that k over m is equal to omega squared. That's what we saw when we were looking at the equations as functions of time. Right? That's what defines a simple harmonic oscillator. And so what I get is I take that constant k over m in front of between the minus sign and the x, and I take the square root to get the angular frequency. So the angular frequency here depends on the spring constant and depends on the mass. For a spring and mass system, that makes sense that that's what the angular frequency would depend on. The period then is just 2 pi over omega, so 2 pi over the angular frequency, and so that's going to be 2 pi over, and now I flip my fraction over, m over k. So one of the things that always causes confusion is making sure that you've got the k on top in the angular frequency and the m on top in the period. So for my angular simple harmonic oscillators, so the simple pendulum. So the first thing, what is a simple pendulum? Well, basically the simple pendulum, anything is a simple pendulum as it swings back and forth if I can act like all the mass is located at the end. So basically this is a way of saying I can treat it as if I have a massless string and then all the mass is down here in what's known as the bob of the pendulum. So if that's the case, then again I can go through and solve for the angular frequency using my rotational version of Newton's second law. I get negative g over L times theta for a small angle approximation, and again I take the square root, and so I get that the angular frequency is equal to the square root of g over L. G is just our normal gravitational acceleration, positive 9.8 meters per second squared, and then L here is the length of the string. So one thing to note is it does not depend on the mass. So if I can act like all the mass is at the end of the string, then I don't actually care how much mass is there. So that's something important to keep in mind. Then the period of my simple pendulum is going to be t equals 2 pi over omega. So again, 2 pi over square root L over G. If I can't act like all the mass is stuck at the end, then I have what's known as a physical pendulum. So here, let's say I've taken some long, thin rod. Here's the center of mass of the rod. But I've got it connected to a hinge so that I can pull it out and then it'll swing back and forth. That's a physical pendulum because I can't act like all the mass is sitting down here. It's clearly spread out uniformly along my rod. So in this case, when I solve my Newton's second law, my rotational version of Newton's second law to figure out what omega is, I get that omega is equal to the square root of mgh over I. And again, m and g, those are mass and gravitational acceleration. But the h here is our distance from the center of mass to the pivot, just like what we saw in the parallel axis theorem. And then I is our motion of inertia about the pivot. And again, the reason I bring up the parallel axis theorem is that this moment of inertia can never be the moment of inertia about the center of mass, or else your physical pendulum wouldn't oscillate. So to have a physical pendulum, you have to have an h here, which means that you're going to need to use the parallel axis theorem to figure out what that moment of inertia is. Again, given that this is my angular frequency, then it's straightforward to figure out that the period of my physical pendulum, t equals 2 pi over omega, so it's going to be 2 pi times the square root of I over mgh. And so those are the three basic simple harmonic oscillators that we'll deal with: the angular frequency for each of them, the period for each of them, and again trying to indicate sort of when each of these is appropriate in terms of thinking about when do I have a simple pendulum versus a physical pendulum versus a spring and mass system.